So
Wait a
our
minute, I
next
didn't-
speaker is Julia Bernatska. She will tell us about Thomae formulas and application to finding reality conditions for integrable hierarchies. So please start your talk.
Thank you, the organizers, for inviting me to this conference, and I'm grateful to all participants who are interested in this topic. So you see here the outline of my talk. I will start with preliminaries, where I describe the family of curves which serve as spectral for several integrable hierarchies, and I will explain how these curves are uniformized. Uniformization is the main part of algebraic integration of such curves. So it's important to introduce some functions in terms of which quasi-periodic solutions can be written. Then I recall the known quasi-periodic solutions to integrable hierarchies and then describe the problem of reality conditions, which include conditions on spectral curves and conditions on solutions, which are expected to be bounded and real-valued. And finally, I will present exact quasi-periodic solutions to several integrable hierarchies, namely the KdV hierarchy, the sine and hyperbolic sine Gordon hierarchies, and also the MKdV focusing and defocusing hierarchies. So we start with a family of curves which serve as spectral for these particular 5 integrable hierarchies which I mentioned before. So this is a hyperelliptic curve with one branch point at infinity. The theory of uniformizing these curves respects the set of weight. And you see here how we introduce this weight and parameters of the curve, which are denoted by lambda, are also assigned the set of weights, and this weight is indicated in the index. We will be talking about spectral curves for integrable hierarchies, which means we have some requirements. First of all, these curves should be real. Simply speaking, this means that all parameters of the curves are real. These parameters serve as integrals of motion, and from the physical point of view, it's quite natural to require these parameters to be real. And this means that branch points could be real or form pairs of complex conjugate branch points. So I separated 3 cases: when we have all real branch points, when we have the maximal number of pairs of complex conjugate branch points, and this number equals the genus of this curve, or it could be a mix of real and complex conjugate branch points. And this statement is the only reality conditions known till recently on spectral curves for integrable hierarchies. When I computed quasi-periodic solutions for several integrable hierarchies, I discovered that this statement is not entirely correct. In fact, this case is impossible. It doesn't work because we come to solutions which are not real valued. So in fact, we have only 2 options: when all branch points are real, and these curves serve as spectral for the KdV, the defocusing MKdV, and the hyperbolic sine-Gordon equation. The 2 last hierarchies share an additional condition. This free parameter vanishes, which means one of branch points is 0. And another option, when we have a curve with the maximal number of pairs of complex conjugate branch points, and the remaining finite branch point is 0. And this type of curves serve as spectral for the focusing MKdV and the sine-Gordon equations and the hierarchies. Now I pay attention to the problem of uniformization. We will work with not normalized holomorphic differentials given in the standard form. Again, the index shows the total weight of the corresponding differential. We compute first-kind periods with respect to these differentials, and these periods form two period matrices of the first kind, and also generate the lattice with respect to which the Jacobian variety is introduced. We define the Abel map in the standard way. The base point is located at infinity. And we will be interested in solutions to the Jacobi inversion problem, which is a problem of inversion of the Abel map. The preimage of a point of the Jacobian variety is well defined if this divisor is non-special. And we will represent such divisors by collections of G points. A solution to the Jacobi inversion problem was known since the 19th century and is given by these two polynomial functions, polynomial in x and y. The first function is a polynomial in x, in fact, of degree g, and coefficients are expressed in terms of multiply periodic p functions with two indices, which generalize the Weierstrass p function. Given a point at the Jacobian variety, we compute coefficients, and then we are able to find roots of this polynomial, and these roots give us x coordinates of points of this divisor, required divisor D. The corresponding y coordinates are obtained from this second function. Let me recall how p functions are introduced. These formulas were given in the monograph of Baker, and he called these p functions multiply periodic functions. As you see, p functions are generated from the sigma function, which is the only modular invariant entire function associated with each curve. The sigma function has a representation as an analytic series and in all its arguments. But this way leads to bad convergence. So p functions obtained in this way will produce an issue with accuracy. So we will use another definition of the sigma function, which connects this function to the theta function with characteristic of the vector of Riemann constants. The theta function is defined on normalized variables and normalized first-kind period matrix, which is known as the Riemann period matrix. So this definition for the sigma function was first introduced by Baker and later formulated more accurately by Buchstaber, Enolsky, and Leikin in this paper. And I ask you to remember this paper. I will refer to it later. If we use this definition in the following definition of the p functions, we come to the expressions which are pretty similar to these. The only difference for p functions with two indices, we have here an additive, terms which are entries of this matrix which produce the quadratic form here. So it's in fact amazing that this multiple, which is an exponent of a quadratic form, turns the theta function into the modular invariant sigma function. So this matrix kappa is symmetric and is obtained from second-kind period matrix eta. So I have to say several words how we compute second-kind periods. We use differentials of the second kind associated with the first kind differentials. So these are particular differentials. They exist a procedure how to compute them. For example, in GNO 3, they look like this. Then we compute second kind periods from these differentials and arrange them in two second kind period matrices. And first kind and second kind period matrices satisfy the Legendre relation, which means this matrix is symplectic. And now we jump to quasi-periodic solutions. I should recall that solutions for some integrable hierarchies, in particular the KdV and the sine-Gordon, were expressed in terms of theta functions, and these solutions are gathered in this monograph. But today I focused on solutions expressed in terms of p functions. And I refer to this paper, which I mentioned before, where you can find a quasi-periodic solution for the KdV equation and a quasi-periodic solution in terms of this p function for this sine-Gordon equation. Though solutions were suggested, the reality conditions were not specified. So this argument U belongs to the Jacobian variety, and it's an arbitrary point where p function is well defined, so has no pole. Moreover, there exist identities for p functions. This is one and another one, which could serve as extensions of the KdV, the sine-Gordon equation, and many others to the whole Jacobian variety. So the problem of reality conditions wasn't solved and even wasn't stated properly. From the physical point of view, it's evident the spatial variable x and the time variable t should be real. And also we expect the solution to be real valued. So we have several questions. First of all, we need to find a path or submanifold in the Jacobian variety which serve as the domain for quasi-periodic solutions. So it will depend on x and t. And also, we would like to prove that on this domain, our solutions, for example, these solutions are bounded and real valued. Okay, it's clear why I'm talking about real valued solutions, but the question is why I'm talking about boundedness. So each quasi-periodic solution is represented by a trajectory of a Hamiltonian system in the hierarchy, and this trajectory has turn points exactly at the branch points of the curve. It means that half periods belong to the domain of these functions. But not all half periods are so that sigma functions doesn't vanish. At some and quite many half periods, sigma function vanishes, and it means that p functions have poles. So we would like to avoid such half periods, and so I will address this problem first, and we solve it with the help of the Thomae formulas, which introduce a one-to-one correspondence between half periods and divisors on branch points. So some half periods correspond to non-special divisors, and these are even non-singular half periods at which sigma function doesn't vanish, and only at these half periods. If a half period corresponds to a special divisor, then sigma function vanishes. Okay, in the case of all real branch points, we have that all entries of the first period matrix omega are real, and of the first period matrix omega prime are purely imaginary. So we obtain a rectangular lattice. You see here a picture in genus 2. This is a projection to the first coordinate in the Jacobian variety. The picture in projections to other coordinates are the same. So all 16 half periods, which we have in genus 2, are represented by dots, blue dots, solid dots, or blue circles. Dots represent even non-singular half periods, which correspond to non-special divisors, represented by 2 branch points. And circle shows positions of half periods which correspond to special divisors, which are represented by one branch point, finite or infinite. And you see that all half periods are arranged on 4 horizontal lines parallel to the real axis. And only one among these lines contain all even non-singular half periods. Similarly, with vertical lines, among 4 lines, we have only one where all even non-singular half periods are located. And we have even an intersection of these 2 good lines, which we prefer to choose, which is located at this point, which corresponds, which is the vector of Riemann constants on this not normalized Jacobian variety. So we obtained 2 subvarieties in the Jacobian variety, which could serve as a domain for quasi-periodic solutions. One is a subspace parallel to the real axis, and another is a subspace parallel to the imaginary axis. What we have in the case of G pairs of complex conjugate branch points. We have a rhombic lattice formed from some rhombic sublattices. The picture is a bit more complicated because we do not have such nice rectangular structure. Again, by blue points, all 16 half periods are labeled. Some half periods appear twice, one time on the horizontal line, another time on the vertical line. By these pairs of points are congruent, so they represent the same half period. And again, you see that all half periods, all 16, are arranged on 4 horizontal lines. And there is only one line with all even non-singular half periods, and the same with vertical lines. So this is true for both cases of possible, yeah, please, any questions? For possible spectral curves. Now we come to the problem of real valued solutions. So here you see how this vector of Riemann constants is expressed in terms of periods. And this vector is complex valued, which means that our argument of quasi-periodic solutions is complex valued in any case, and we will use the addition law to prove that solutions are real valued. So, analyzing the addition law, we find that in the case of all real branch points, all p functions with 2 indices on the possible domains are real valued. P functions with 3 indices on the subspace parallel to the real axis are real valued, and on the subspace parallel to the imaginary axis are purely imaginary. And we use these facts to prove, which is quite evident, that this solution to the KdV equation is real valued. And it's also bounded due to this form of the domain, of the argument. Now we can write down the solution for the hyperbolic sine-Gordon equation. So this function is also real valued and bounded. And S, this vector, has x at the first position and t at the last position. This comes from the construction of the hierarchy. Now let's talk about spectral curves with G pairs of complex conjugate branch points. And let me recall that the remaining branch point is 0. From the construction of the hierarchy, we obtain the following identity, which guarantees that this function is real valued. So we have to prove this, and I was able to prove this statement using the addition laws in genera 1, 2, and 3. Okay, I'm sure that it works for high genera, but I didn't find a general solution. So this remains an open problem. And now I would like to present my last result, maybe the most essential a quasi-periodic solution for the MKDV equation. So we consider the both cases of the defocusing and focusing MKDV equations. In the defocusing case, the spectral curves have all real branch points and one fixed at 0. In the focusing case, we have spectral curves with G pairs of complex conjugate branch points and the remaining point at 0. And then quasi-periodic solutions on a curve of any genus is represented by this expression. So you see how argument looks like, and this coefficient differs for the focusing and focusing case. Again, by the addition laws, it is possible to prove that this function is real valued, and we know that it's bounded because our argument had the following form. Okay, so I should say that this is the first known solution to the MKDV. No solutions were presented before in the literature. So that's all. Thank you for your attention.
Thank you for your nice talk.